Video 28, 4.4, the fundamental theorem of calculus, day 4. So today we're going to talk about the second fundamental theorem of calculus, and this deals with taking the derivative of an integral. So if a function f is continuous on an open interval I containing a, then for every x in the interval, we can say the derivative of the integral from a to x of f of t dt is equal to f of x. So this is saying the derivative of the integral, okay? That's what d dx represents. All right, so we'll kind of walk through this so it makes a little bit more sense, but something that you need to keep in mind is that derivatives and antiderivatives are inverses and they cancel out, okay? So if we're going to take the derivative of this portion inside, all right, that's essentially what we're doing here. So we're going to see what that gets us to. So remember the definite integral as a number where we have the integral from a to b where a and b are constants and f is a function of, x is a function, or f is a function of x, okay? The definite integral as a function of x is going to look like this. Big F of x is equal to the integral from a to x, where x is a variable, of f of t. So f is a function of t this time. So let's take a look and break this apart. So there's kind of two different scenarios with this second fundamental theorem of calculus, all right? So the first one is when if we let big F of x equal the integral of little f of x dx, okay? Remember, x is a variable and a is a constant. So scenario number one, if we take the derivative of the integral from a to x of f of t dt, forget about the derivative at this point. Let's just focus on integrating this portion, okay? So we're going to integrate this f of t dt from a to x. Okay, so when we integrate this, we get big F of x minus big F of a, right? Because this is essentially equal to f of t evaluated from a to x. Okay, so now what we're going to do is we're going to take the derivative of this. So when we take the derivative of f of x, we get little f of x. When we take the derivative of f of a, remember a is a constant, so this is just going to be a constant as well. So when we take the derivative of this, we get 0. So this allows us to conclude that the derivative of the integral from a to x of f of t dt is simply f of x, meaning I'm just going to take this x and plug it into the function that's in terms of t. Now we look at the second scenario where we're taking the derivative of an integral from a to now g of x, so now another function of f of t dt. So we think about it the same way when we integrate this, and this is like saying f of t, and we're going to integrate that from a to g of x, okay? So when we go ahead and plug things in, right, that's going to be f of g of x minus f of a, and now we're going to take the derivative of this. Well, when we take the derivative of this portion right here, we're going to get little f of g of x, but we can't forget about that chain rule, so now we have to times it by g prime. All right, when we take the derivative of f of a, remember this is just a constant. So taking the derivative of a constant, we're just left with 0. Therefore, we can make our conclusion that the derivative of an integral from a to g of x of f of t dt is equal to f of g of x, so simply plugging this function into t, times our chain rule, the derivative of this green guy. The next thing we're going to talk about is the net change theorem. So what is the net change theorem? The definite integral of the rate of change of a quantity f prime of x gives the total change or net change in that quantity on the interval. So for instance, this is just what the fundamental theorem of calculus is telling us. It's telling us to integrate this from a to b. Okay, knowing that we are integrating a derivative. So when we're integrating a derivative, we're back to the original function. So that's f of b minus f of a. So another way we can think about this is where we end, right? And this is what the start was. Okay, so that's our net change of f. So another way we can think about this is f of b is equal to f of a plus that integral of f prime of x. Now we're going to get to some examples. We're going to use the second fundamental theorem of calculus to find f prime. So if we take a look at this first example, f is equal to the integral from -2 to x of t squared minus 2t dt. So this is a function in terms of t. So we want to find f prime. So we want to take the derivative of the left side, which means we want to take the derivative of this integral. So taking the derivative of this integral, I notice that we're integrating it from -2 just to x. So remember, that portion of the second fundamental theorem of calculus says f prime of x is equal to the derivative of the integral from a to x of f of t dt simply equals f of x. So all we're going to do to find the derivative is we're going to take this x and just plug it into that function. So by the second fundamental theorem of calculus, SFTC, we get f prime to equal x squared minus 2x, simply substituting the x for the t. This second example, we should notice now we're taking, or f is equal to the integral of from 2 to x squared. So how does that change it? Well, this is just saying, oh, well now our second limit is going to be a function in terms of x, right? Not just x, it's just x squared. So we have to remember this chain rule aspect of it. So when we take the derivative, we're taking the derivative of this integral. So the first thing I'm going to do is so that is equal to now 1 over, I'm going to substitute x squared in for t, and now we can't forget about our chain rule. So we're taking the derivative of x squared, so times 2x. When we clean this up, we should get 2x over x to the 6th, which is simply the same as 2 over x to the 5th, or you might see it as 2x to the -5th. Okay, so there we have it. Let's move on to the next example. Before moving on, make sure you pause the video and get all of these reminders down. So something to remember, that s of t is equal to the position function at time t. V of t is our velocity, which is the derivative of s of t. A of t is our acceleration, which is the derivative of our velocity, or the second derivative of our position function. Okay? Taking the integral from a to b of our velocity gives us our position function, but we can think about this as our displacement, okay, when we're talking about particles. And remember that the integral from a to b of our acceleration gets us back to our velocity. The integral of our velocity gets us back to our position. And then one other thing we have to remember is the total distance. Total distance is equal to the integral of the absolute value of our velocity. So make sure pause the video and get that all down. Okay, so let's get into this example. The velocity function in feet per second for a particle moving along a straight line is v of t equals t squared minus t minus 12. For 1 is less than or equal to t, which is less than or equal to 5. So we want to find the displacement. So when it asks for the displacement, remember our little side note over here, displacement is simply the integral of our velocity, okay? So in this case, when we're finding the integral of our velocity, We are given our velocity function, and we are given our interval that we're on. So we're going to integrate from 1 to 5 of that velocity function. And when we integrate that, we get 1/3 t cubed minus 1/2 t squared minus 12t. And we're evaluating that from 1 to 5. So remember, when we plug 5 in, that's the end value. And then when we plug 1 in, that's where we're starting off. So we want to find this displacement. So the end minus the start. And when we do, we get negative 56/3. So what does that tell us? What that tells us is that we moved to the left 56/3 feet. Or we can think of it as 18 2/3 feet. All right, so we moved left. That's what that is telling us. The next part asks us for the total distance that the particle travels. So remember, total distance is equal to the integral of the absolute value of our velocity. So we're looking at this, the integral from 1 to 5 of the absolute value of t squared minus t minus 12 dt. So I just graphed this, but remember, because it's the absolute value, we have to kind of redraw our graph. So I'm going to zoom in over here, and anything that's negative, because we're talking about the absolute value, is going to have to go positive. So what we're really looking at, and I'll redraw the graph in blue. So now all this negative stuff is going to come back up here and be like this. So the graph we're really looking at is this in blue here. Okay, but now we're going from 1 to 5, so we have to manipulate our integral a little bit. Okay, so if we're going from 1 to 5, that's this piece here, and we want to find the area under the curve. So what we should notice is the integral from 1 to 4 has changed, right? Now, before it was underneath that x-axis, but taking the absolute value, we now moved it above. So that's going to equal the opposite of that. So it should be the opposite of t squared minus t minus 12 dt. And then we're going to add that to this portion over here, the integral from 1 to 5, which hasn't changed. So the integral from 1, or sorry, not 1 to 5, 4 to 5 of t squared minus t minus 12 dt. All right, and now we're just going to integrate this. So when we do, we should get this blue portion to be negative 1/3 t cubed plus 1/2 t squared plus 12t. And we're going to evaluate that from 1 to 4. And then we're going to add that to 1/3 t cubed minus 1/2 t squared minus 12t. And we are going to integrate that from 4 to 5. Okay, and when we do, you can check my math on all of this. I believe we get 104/3 minus 73/6 for that first part, plus we'll get negative 185/6 minus minus a negative 104/3 for the second part, and what that comes out to be is 79/3, or 26.3 repeating feet. So that is the total distance that that particle traveled. This last example deals with our net change theorem. all right, which remember, that's the fundamental theorem of calculus, but we're just looking at it in terms of net change. So remind yourself that our net change theorem is right here, okay? The integral of our derivative is equal to our function evaluated from b to a, or a to b, I should say, so our end and our start, or we can think of it as our end value is equal to the start plus the integral from the interval a to b of that derivative. So let's take a look at our example. Water flows from the bottom of a storage tank at a rate of RT equals 200 minus 4T liters. So when you see rate, we're thinking derivative, okay? Liters per minute, where T is between 1 and 50. If 3,000 liters have flowed from the tank after 1 minute, so that's our starting value, that's how we can read that, find the number of liters that have flowed after 6 minutes. So since we know, or our interval is from 1 to 50, we need to know, well, what happened in that first minute from 0 to 1? And that's what this piece right here is telling us, okay? So that's how we interpret that. So let's go ahead and let W of T be the amount of water in the tank at time T. R of T is our rate, so we can think of that as the derivative of W, okay? And it's the rate at which water flows into the tank at time T. So W of 1 equals 3,000. We can think of this as like our starting value, right? This is like our F of A, okay? All right, so now let's move on. So now we want to find the number of liters that have flowed after 6 minutes. So we want to find W of 6. W of 6, that's like our F of B value that we want to find. Okay, so we set it up. Let's go ahead and zoom in a little bit. Okay, so when we set it up from 0 to 1 of 3,000 dt, that's our starting value. Remember, that's what we said. That's like our F of A or our W of 1. So we know that that's going to be 3,000. So the first minute, there's 3,000 liters. And now we have to integrate from 1 to 6 of that rate. Okay, so here we are integrating from 1 to 6 of 200 minus 4t dt. So go ahead, finish this up, and come back and check at the end. Hopefully you got 3,930 liters. So if you integrated our rate, you should get 200t minus 2t squared. Evaluating that from 1 to 6, you end up with 930, but we have to add that to our F of A value, 3,000, to get our final answer. If you have questions on any of this, make sure you ask those in class.